All right. So I know you've had a guest lecture about recursion, but you know I'm kind of a controlling guy and I like to do things myself. So just a couple of, we'll start with some simple things. And some of this goes back already to something we did very early in this course where we were looking at the model of memory and variables and what happens when you change an array and when you assign something to an array. But let's start with just something simple here. Okay, so I wrote a function called test I. Or test takes an argument called I, and it prints the value of I. So if I call test 10, it prints the value of 10. Okay. And now, what happens if I say print I?
String I.
What's that?
The string I.
Well, if I press enter right now, what's going to happen? Yep. It'll give me an error. It'll say I is not defined. So why is it that I was defined here, and that just executed and it printed 10, but it's not defined here? Can someone give me a concise reason? Yeah?
It's because 10 was an integer, and if you wanted to print I, you have to put quotations on it. Because it thinks I is a variable right now.
Yes, but I mean that's the exact line of code that was here. So I was a variable there. Why did that work and this doesn't? Because of the scope of the variable. Yeah. So what happens every time we call a function in Python, and this is important to understanding recursion, is when I call a function, you know, there's this. Let's say, I'll say global. There's this sort of global space for names of variables. And right now, when I'm at this command prompt, this command prompt here, that's the space I'm in. And in this space, there's some variables defined. Mostly, well, one of them is test, and there's lots of other ones that are built in, but there's no variable called I defined in this space. Now, when I call the function test and give it an argument, what happens is a new thing gets created, and that thing is called a frame, or a stack frame, and it's a little space that's just allocated for this test function, or this particular call to this test function. And this test function takes an argument I, and so that introduces inside that frame a local variable called I, and I'm calling it with the value 10, so I get set to 10 in that frame. And then the function starts executing. So the body of the function, that's this one line here, starts executing. And the body says print I. So Python sees, okay, I'm making a function call, print, to a function called print, and I'm passing it one argument, and that argument is, looks like a variable called I. So it goes off looking for that variable. And where does it look? Well, the first place it looks is right here in this stack frame. Okay. And it says, I found this variable I, its value is 10, so what I'm really going to call is the function print with the value of 10 as its argument. That's why that works. Okay. And then implicitly here, once this function is done executing, so it finishes, it returns. And as soon as a function is done executing, its stack frame disappears, goes away. And that's why at this point, if I call print I, Well, the same set of things happens. Python reads this and says, okay, it looks like a function call, and the function that he's calling is called print, and it's taking an argument, and that argument is a variable called I. Let's look for the variable I, and it goes looking, and it doesn't find it anywhere in this global stack frame, and I get this error that says I is not defined. Okay? Is that clear? I think you kind of all sort of knew this, but never really thought about it carefully. All right, let's try something a bit more sophisticated. So you saw from the previous lecture on recursion that usually when you use recursion, there's kind of two pieces that you need. You need what's called a base case, which is something that stops the recursion from going on forever, and you need a recursive call, which is just calling the same function again. So let me just write this, and we'll see what happens. All right, so here's a function called count. It takes an argument n, and we can just read off the code. If n is equal to 0, it just returns. So let's try that. Count 0, nothing happens. And if n is not equal to 0, then it prints the value of n, and then it calls itself with the value n minus 1. Okay? Is that clear? So what happens if I call count 1? Who wants to tell me what will happen? Yep. So it'll print 1 and then return. And if I call count 5, yep.
Shouldn't it print 1 to 5? Or is it 5 to 1?
Good question. The suggestions are it'll print 1 through 5, or it'll print 5 through 1. 5 through 1. That's right. Okay? And in this stack frame picture, this is what's happening. We start out, as we are now, in this global stack frame. Nothing special is defined. And then we call count 5. So that's a function call. So it creates a new stack frame, just associated with this particular call to count. Count is a function that takes one argument n, and we're calling it with that argument set to 5. So it creates the stack frame for this function with n set to 5. Okay. Now, 5 is not equal to 0, so this doesn't execute. Instead, it prints the value of n. So let's see what's being work our way through this. So it prints the value of n, which is 5 at this point. And then it calls count n minus 1. What does that do? Well, that's a function call. Function call always creates a stack frame. The value of the argument to that function call is n minus 1. Now, n up here is 5, minus 1 is 4. So when we call this new function, the value of n is 4. Okay. So now we have two stack frames for count. And this thing is called the top of the stack, but we think of it as the most recent one. In the most recent one, the value of n is 4. In the slightly older one, the value of n is 5. Now, we're now executing in this stack frame here. We're executing the body of this thing. So n, which is 4, is not equal to 0, so that doesn't happen. Instead, we print the value of n. That's when 4 comes out. And then we call this function again. That creates a new stack frame. That function takes an argument. And the value of that argument is now 4 minus 1 is 3. Okay. And this goes on again. 3 is not 0. So we skip that part, and we print 3, and then we call count with an argument of 2. 2 is not 0, so we print it, and then we call count with the value of 1. 1 is not 0, so we print it, and then we call count with the value of 0. And this is what our stack looks like now. This whole thing here, that's what's called the stack. And these little pieces here, these are the stack frames. Okay. And now finally something different happens. In this case, 0 is equal to 0, so we just return. And what happens when we return from a function? That function's stack frame disappears, and we continue executing wherever we were executing in the whatever the function that called this one. But that function just finished calling count. It just executed its last line of code, so it just returns. And then this returns to this function again. This returns, this returns, this returns, and finally this returns, and then control returns back up to us at the global scope here. So we're back in the interpreter again. Is it clear what happened there? Yeah.
Is this where recursion is slow? Because for large enough values, it creates a whole lot of stack frames?
Recursion is not terribly slow. I mean, if recursion is making things really slow, it's because it's something. It's a problem that's not really inherent to recursion. It's a different problem, and we'll talk a bit about that sort of efficiency issues. But this is not a terribly inefficient implementation of count. So, well, we know what this one does now. Let's call it count down. Oops. You always have to be careful when renaming recursive functions, because you have to remember to rename the recursive calls inside of them as well. So that's a function called count down. We'll save that one. So what happens now? Here's another function called count. First of all, what's the difference between that one and the old one? I mean, but just looking at it, what's the difference? Don't try and reason out what's happening. Just tell me what. So someone did this. Yeah. So 2 lines of code change order. In the original one, I first printed the value of n, and then I recursed on n minus 1. In this one, I recurse on n minus 1, and then I print the value of n. So What happens now if I call count 5?
There's no question.
What's that?
They're not 25, it's just 10, just 4, I guess.
So the first thing that gets printed is 4? Why 4?
Because it's minus 1 first.
Okay, but before 4, what happens? If it doesn't print 5 first, because it first recurses on n equal to 4, then why would it print 4 first? Because before it prints 4, it's going to recurse on 3. And before it prints 3, it's going to recurse on 2. And before it prints 2, it's going to recurse on 1. Before it prints 1, it's going to recurse on 0. And then it's going to start returning. So this actually counts upwards. So 1 is the first thing that gets printed. Okay? And so this here was the trace of count down. What's happening now with this new version of count? Well, we call it with n equals 5. That creates a new stack frame with the value of n set to 5. 5 is not 0, so we don't return right away. Instead, we call this thing with the value 4, which creates a new stack frame with the value 4. 4 is not 0, so we don't return. Instead, we call this thing again with the value 3, which creates a new stack frame with n set to 3. 3 is not 0, so we call it again with n equal 2. 2 is not 0, we call it again with n equal 1. 1 is not 0, so we call it again with n equal 0. And then finally, this code in the base case executes, and we return immediately without printing anything. So that means this stack frame disappears, the one where the value of n is set to 0. And we resume execution in the function call when n is set to 1. And where do we resume execution? Well, right where we left off, right after the function call we just made. So we just called here count of 0, so we'll execute the next line of code, which says to print n. And right now n is equal to 1, so the first thing we ever print is 1. And then we return. Now we're back up just after this recursive call again, but in a different stack frame where the value of n is equal to 2. So then we print 2. And then we return. And now we're back up right after the recursive call, but in the stack frame where n equals 3. So we print 3. And then we return, and so on. Then we print 4, and then we return, and then we print 5, and we return. And here we are back out at the outer layer. In this case, it's in the interpreter. And yeah, there's no n's to be found anywhere out there, because even though at some point there were actually 5 different variables called n, by now they're all gone. That makes sense? In fact, there were 6 different variables called n at one point. Is that clear? Yeah?
So how is it possible to keep multiple values named n at the same time and then reference them without kind of forgetting them?
You can't. So, I mean, the short version is when you look up a variable like this, so when I just say print n or put n in an expression, n plus 2 or something, the standard lookup mechanism takes effect, and it looks in the most recent stack frame. And actually in Python, it won't even look in higher up stack frames. It either finds it in the current stack frame, or it goes up to the global thing. Okay. That can be different for different languages, but Python's what's called it uses what's called static lexical scoping. So this function count, if you look at where it was defined, well, I defined count inside this, basically at the outermost level in the global frame. So the first place it looks will be the stack frame for count. If it doesn't find a variable there, it'll look in the global stack frame. Okay, so we can test that. So this is called count up. So just to illustrate that. I think Python even has a safeguard to avoid these kinds of things. Yeah, no. So Python 3 has a safeguard to avoid actually making those kinds of mistakes even. So it only wants you to look in local scope. If you want to look outside of there, then you first have to declare the thing as global coming from elsewhere, and then it'll look up in the global scope. Okay. So the short answer to your question is you can't. There's a bunch of different values of n there. At any time, I can only access one of them. Okay. How about this version of count? What will it do? Any guesses? Yep. Yeah. So this version prints the value of n that it's given before recursing. So if I call it with count 5, well, the first line of interesting code will be this one that prints 5. And then it recurses. And then the next line of interesting code will be the one that prints 4. And then it recurses. And the next line of interesting code will be the one that prints 3 and 2 and 1 down to 0, where it will return. And now each of those function calls, right, there will still be on the frame, like on the stack, there'll be a frame with n equals 1. So when n equals 0 returns, this frame is still on the stack, and that function is still executing. In fact, that function just finished its recursive call, so it's going to execute the next line of code, which is to print the value of n. And in this case, the value of n is 1. And then that function returns back up to the function where the value of n was 2, which still has one more line of code to execute, which is to print the value of n, which is 2, which will print 3 and 4 and 5, and so on. So this will count down, 5, 4, 3, 2, 1, and then count back up, 1, 2, 3, 4, 5. So you're watching it go down the recursive stack, down the recursion, and back up the recursion. Okay. Is this too easy? I think if it were too easy, everyone would be able to tell me the answer immediately. So recursion is something to get your head around. It takes time. So these are sort of some warm-up exercises. Here's one that you were shown already. So factorial, remember, is supposed to be this function that takes n times n minus 1 times n minus 2 times n minus 3 times all the way down to 1. For example, if I say factorial 5, then I want to see 5 times 4 times 3 times 2 times 1. And this is a natural candidate for recursion. So how would we write this recursively? So when you write recursive functions, depends how eager you are. I tend to get excited and think about how I can solve it on a smaller problem, solve a smaller thing first. If you're more cautious, then you should think about, well, how do you solve the smallest thing first? So, so somebody tell me what to write. Yeah.
If n equals 0, return 1.
Okay. So if n equals 0, then I'll return 1. Now you'd have to go and look in a math textbook to see if that makes sense, if the 0 factorial is equal to 1 or not. Standard interpretation of factorial is it's the number of permutations of n items. And so the number of permutations of 0 items is, well, there's sort of only one. There's nothing. It's like how many sort of empty lists are there? Well, there's one empty list. There's nothing to distinguish an empty list from another empty list. So indeed, the base case n equals 0. The correct mathematical definition is to return 1. Otherwise, okay, so we handled the easy case. Now all we need to do is express the general case, which is factorial of n. That's this thing. That's what factorial of n should look like. Can you split that into 2 parts, one of which is somehow factorial of something smaller? Or if you like, here's factorial of 5. Do you see hidden in there the factorial of something that's smaller than 5? Well, 1, yes, but what about this little bit here? Yeah. 4 times 3 times 2 times 1, hey, that looks familiar. That's 4 factorial. And n minus 1 times n minus 2 times n minus 3 times so on all the way down to 1, well, that's n minus 1 factorial. So factorial of n is just n times n minus 1 factorial, except when n is really small, in which case we fall into this base case. Okay. Let's check that. What's 3 factorial in your head? 6. It's 3 times 2 times 1. That's 6. Good. What's 10 factorial in your head? I'm kidding. Gets big quickly. All right. And what about 100 factorial? No problem there. Does it look fishy? No. I mean, it looks, to me, it seems to look weird, but that's only because you're not used to looking at, the actual expansion of these factorial functions. I mean, it feels fishy that this number, which is 100 times 99 times 98 and so on, ends with all of these zeros. But if you think about it for a while, you know that this number has to be divisible by 10 because 10 is one of its factors. And it has to be divisible by 30 because 30 is one of its factors. And in fact, it has to be divisible by 10 and 30, so it has to be divisible by 300. You realize actually all of these numbers will, once n gets big, these numbers finish with a lot of zeros. Nothing magical about 100. We can put in our favorite thing. There's a lot of zeros at the end. Okay, so that's how we do factorial. And now we can start to get crazy and say, wow, I love recursion. I can do so many things with it. Let's do everything with recursion. Let's compute the sum of all the values in A. Ignoring for a second the fact that Python has a built-in function called sum that does exactly this. Let's do it ourselves because we love recursion. Okay, so you give me a list, A, and I want to add up all of its values. So that means I want to return A at 0 plus A at 1 plus A at 2 plus and so on all the way up to the length of A minus 1. Do you see any way of expressing that recursively? Well, we can either be eager and do as I'm always eager to do, which is to take this thing and break it up into a recursive part and another piece that we just add on. Or we can think about what's the really easy case. When do we know how to do this very easily? And it's sort of the base case. When is it easy to return the sum of things in a list? Like when do I not even have to add anything together to give you the sum? Yep. Well, when the length of the list is 0, that's one thing that's easy. What's the correct answer in that case? What's the sum of no things? That's a little less mathematically clear. So if you think of like sums, like if you've taken discrete math, this summation notation, then yeah, the empty sum is 0 seems to make sense. Is there another case where it's really obvious what it means? Yeah. So if there's only a 0th element, means the list has length 1. So if the list has only one element, then I can still give you the sum without actually adding anything together. I just give you the one thing. So here I'll just put a comment. This is open to interpretation. But, okay, so if the list is empty or the list is of length 1, I know what to do. Otherwise, yep. Okay, so you want to write something like this. Now, so that's sort of the general flavor of it, but here we don't really want to, I mean, if A is a list and we add something to it, we're going to get another list. So it's the right flavor, but not quite. What we want to do is we want to take a nibble out of A. That's what's here on the left. Just take a bite out of A, and then recurse on the rest, everything except that bite. So there's a few ways to do that. One way I can think of is to say, well, the bite that we'll take is we'll eat A at 0, the first element. We know now that that exists because the length of A is not equal to 0, so we know that that exists. And A minus 1 here, so that doesn't quite make sense for us. That doesn't make sense to subtract 1 from a list. But we mean something whose length is smaller by 1, and something whose length is smaller by 1 can be this thing. The list A, or the sublist of A that starts at element 1 and goes all the way to the end. That one is shorter, right? That has length 1 less because it's missing A at 0. Okay. Let's see if that works. 0, 1, 2, 3, 4. That'll be 3, 6, 10 should be the answer. Indeed, that works. Okay. And we can check if I give it an empty list. Yeah, it gives me 0. And if I give it a list with only one value, it gives me that one value. Right? Is that... is that clear? Okay, so looks like we know recursion, right? We understand what's going on here. So let's try and let's test some of the things we've written. Like this factorial function. It can do factorials for really, when the results are really big, 200, 500, 998. Oops. What happened? Anybody know? Yep. Maximum recursion depth exceeded. In comparison. That in comparison is a bit of a red herring. It's the maximum recursion depth exceeded that's the real clue here. And if we look at this thing, that's interesting. It's not a very useful error message. So what we see is that, you get this thing called the traceback. And you may have noticed, if you've done anything even a little bit complicated, the traceback is actually giving you the list of stack frames. So it's telling me that, okay, the error happened here in this call to factorial. And what called factorial? Well, factorial called it. And what called that factorial? Well, factorial called it. And what called that? Factorial called it. And you'll see actually there's a little note in here that says, well, actually, it has abbreviated this error message because that previous error message about being in line 29, well, that should have really been repeated 995 times. So if we were to draw these stack frames, we would see, we started out at 998, and then we added another one with 999, another one with 998, 997, 996, 994, 995, and we got pretty far down, and like we did this 995 times, and eventually this thing said, okay, stop. I'm not making any more stack frames for you. This is more stack frames than I want to make. Python suspects that maybe we've made an error in our code because recursion of this depth is usually not so common, and it just stops us. Okay. And it does that for a good reason. Sort of runaway recursion is the source of problems. There's a very good story, but it turns out not to be true, about, it's true in the sense that a software expert came and testified about it, and I think some court decisions were made on it, but it turned out to be not false. Maybe before you guys were born or before you guys paid attention to these things, Toyota made a whole batch of cars that they had the runaway accelerator problem. You may have heard of it. You would step on the gas or not step on the gas and the car would take off, and there wasn't much you could do about it. And a software expert actually testified about this. So it's a big investigation, of course, lots of lawsuits because people were injured, people died, all of these things. And a software expert pointed it down to what's called a stack overflow, which is what we were leading to here. We had a bunch of recursive calls, 990 some of them. Their stack was growing and growing and growing and growing. And Python says, okay, I'm going to stop this before a stack overflow occurs. But in these embedded systems that live inside your car, like the little computer that's in your accelerator and the little computer that's really good timing because my car is currently at the dealership being serviced right now. I'm sure that's the dealer calling me. Telling me, so these systems don't have those kinds of safeguards. They're super raw, tiny little things. And if the stack grows too much, then the stack is using up memory somewhere, and it starts to use memory that's actually not reserved for the stack. And so that means it's just writing some data somewhere. And this expert had deduced that actually what was happening is the stack was overrunning, and it was writing to a location in memory that was to do with the state of the gas pedal at that time. So saying, okay, writing some bit of information that said, okay, he's pushing on the gas pedal this hard right now, and the car would read that piece of memory and say, okay, he's pushing on the gas pedal, I'll accelerate. It's a really nice story, but it turns out it's not actually true. It was debunked. It was actually just a piece of sticky plastic inside the accelerator that would get stuck sometimes. Anyway, but dangerous things can happen because of runaway recursion, and Python safeguards against that by basically blocking it off. And now factorial, okay, that's one thing. Can we see where it happens with these other functions we've written. So we've done this summer function, right? So A can be a list obtained from a range of length 500. Summer of A, that seems to work. If A is a list of length 800, summer of A seems to work. What if A is a list of length 995? Summer of A seems to work. But if it's so somewhere between 998 and 999, we get this crash again. And if we think about it, that's because if I drew this picture for the summer function, if I drew these stack frames, I would see, yes, there's one call where you're given an input list that has length 999. That makes a recursive call where the input list has length 998. That makes a recursive call where it has length 997. So we get it 900, nearly 1,000 of these stack frames piled up on top of each other, and then Python says no more. That's enough. Maximum recursion depth exceeded. Okay. All right. Well, so you might say now, well, I just fell in love with recursion because it looked like I could do anything with it. And now it looks really disappointing to me because I can't even process lists of length 1,000 using recursion. I mean, that's disappointing, right? 1,000 is not a long list. In the era of big data, 1,000 item list is nothing. So let's think about whether there's a way we could shoehorn this into dealing with longer lists before we run up against this barrier. Okay. So I want to rewrite this summer function. We'll call it summer2. And the only thing I want to change is what's happening here in this last line, in this last recursive call. So what are we doing in that last line? Well, we're taking a little byte out of A0, and we're recursing on the rest. And if I do that, if all I do is byte one element out of A, then the depth of the recursion is certainly going to be the length of A, right? I mean, I start with a list of length 1,000, and then I take off one element, and then I'm recursing on a list of length 999. And then I take off one element, I'm recursing on a list of length 998. So biting off one element at a time, it's going to crash as soon as I give it lists of length 1,000. How could I do it better? Yeah?
Does it make a difference if we start with the first bit, in other words, the first element, or if we take the whole thing and do it from the end?
What's killing us here is just the depth of the recursion, so the number of stack frames that are alive at any given time. And right now, if I give you a list of length n, then that depth of recursion is going to be, it's either going to be n or n minus 1, roughly, at the deepest point when I get all the way down to having eaten the list. Well, let's try something a little bit silly. So biting off one thing at a time doesn't seem to work. So let's just do the dumbest thing we can think of and bite off two things at a time. Okay. Let's think about this. And I need to call summer2. So I check that if my list has length 0, I return 0. If my list has length 1, I return the single value in the list. Otherwise, the length of the list is not 0 or 1, it's at least 2. So that means that A0 and A1 definitely exist. I'm not going to get an error here because by indexing things out of bounds, because I know the list has at least 2 elements. So I'll add up those two, And then I'll add up, so that's these two here, and then I'll recursively add up everything in the rest. Is this going to help? So our original one crashes on a list of length 1,000. Didn't crash on a list of length 995, though. What about this new one? If I give it a list of length 1,000, then what's this depth of recursion going to be? How many stack frames will I get? To know if it crashes, we can run it. It doesn't crash. So why doesn't it crash? Yep. Only 1,001? What about 1,020? So you said that I took a larger byte, but did I take, because instead of taking one thing off, I took two things off. But did I only do that once? So if I start with a list of length 1,000, and then I take two things off, and I recurse on a list of length 998. But when I recurse, it's the same rule. I take two things off, I recurse on a list of length 996. And then I take two things off that, I recurse on a list of length 994. So at each step in the recursion, I'm taking two things off the list. So if I start with 1,000 things in the list, I only have to do this 500 times. Is that clear? So that's why this is working now, but how long is this going to work for? Where is this going to break? Yeah? So 1990, a list of length 1990 works, but a list of length 2000 fails. We made it a little bit better, but it only makes, by biting off two elements at a time, yeah, that helps a little bit, but it doubles the size of the list we can handle this way, but still 2000 is not great. We'd like a more, so if you say I want to go up to 3,000, then I think you would know what to do. In here you put A0, A1, and A2, and then recurse on this thing. But that means you need an extra base case because you can no longer handle lists of length 2 anymore because they're a special thing, right? So you'd have to add another base case. And that would only get you up to 3,000, and then your code's getting longer and longer. That's not what you want. Is there another way we could structure this last line of code? How about the following? I'm trying to compute this thing, right? And I've been looking at solutions where I bite a little bit off of here and then add something onto it. Here's another idea. How about I take all of this and add it up, and I take all of this and add it up, and then I add those two things together. I add up everything in the first half, I add up everything in the second half, and then I add those two things together. So, nice thing about Python is all these things are really easy to implement. Okay, so everything in the first half is just a up to the length of a divided by 2. And everything in the second half is just a at the length of a divided by 2 up till the end. And I should give this another name. Call this summer 3. All right. So, who thinks that this will work for a list of length 2000? Show of hands. Guess. Works for a list of length 2000. Who thinks this will work for a list of length 2 million? Nobody? One person? Works. 20 million? Takes a while, but I don't see it crashing. And eventually this will, there you go. It works. So how does that small change affect things? I mean, how can that make such an enormous difference? Well, let's think about it for a second. So I'm actually doing 2 recursive calls here. So let's look real carefully. And let's do, I don't know, the most baby example where we start with the list A of length 8. Okay. So what does that do? All right, so that, I call this summer 3 on A. A is a list of length 8, and it contains the elements 0, 1, 2, 3, 4, 5, 6, 7. All right. Is the length of A equal to 0? No, it's of length 8. Is the length of A equal to 1? No, it's of length 8. So, since neither of those two things is true, it hasn't returned yet, it's going to make these recursive calls. Now, this is just an expression. We're adding two things together. When you add two things, Python just evaluates them left to right. So the first thing Python has to do is evaluate this part of the expression, the left-hand side. And it does that, and that's a recursive call. So that's a recursive call to summer 3 on the first half of the array. So that creates a stack frame where A is now 0, 1, 2, 3. Okay? And this is what's executing right now. We're still paused here, back in this one. This call to summer 3 is paused, waiting for the recursive call to finish. Well, what does that recursive call do? Well, this is not of length 0 and it's not of length 1, so it's going to make its own recursive call. And in fact, it's going to do two of them. And it's going to call first on here with A containing only 0 and 1. Okay. What about this thing? Well, this is not, so this is what's executing now. This one is paused. This is neither of length 0 nor of length 1, so it's going to make its own recursive calls, and it's going to make one of those recursive calls on the first half of its list. So it's on the list containing only one value. All right? Now, this is one value. This is a list of length 1, so it's just going to return that value. So this quits, it leaves, and it returns, and the value that it returns is the one value in its list, which is 0. Okay. Now we're back up here, where this thing is executing. So what did this thing just do? It just finished this recursive call to its first half. Now it has to make this recursive call to its second half. So it makes a recursive call. That means it introduces a new stack frame. Looks like that. That thing has size length 1, so it doesn't make any recursive calls. It just returns the one value that it has, which is 1, and takes that stack frame off the stack. Okay. Now, we're back up here, still executing this thing, which was evaluating this whole expression. It evaluated the left side, it evaluated the right side. Now all it has to do is add those two things together and return. So it adds those two things together. That's 0 is what came from the left side, 1 is what came from the right side. So it adds them together and returns. That's 1. And it's gone. Okay. Now we're back up here where this thing was executing. It's only evaluated the left-hand side of its expression. It has to go through the whole process of evaluating its right-hand side, which is a recursive call with the second half of its elements. This is A is 2, 3. Now we're executing here, which has to, it's not a list of length 0, it's not a list of length 1, so it's going to do this with 2 recursive calls. One on the list that contains only 2, which immediately returns the value 2. And it makes another recursive call on the list that contains only 3, which immediately returns the value 3. Now, this one has just made its 2 recursive calls, this side and this side. Now it just needs to add them together. It does that, and it returns the value 5. And it's done. And now we're back up here where this thing has just finished its 2 recursive calls. One gave back the value 1, the other one gave back the value 5. It adds those together, and it returns the value 6, and it's done. And now we're finally back up at the parent, where it's got to make its second recursive call on 4, 5, 6, 7. So do you need me to continue at this point? Okay. So this will go and it'll make that tree that looks like that. Okay. And so why did I go from drawing this stack as a big long list of things, one on top of the other, to drawing a tree? Well, because at any given time during this recursive process, there was just one sort of stack path back up of this thing, and then sometimes stack frames just die and disappear, and then they get replaced by other ones. But if you think about how all of this takes place over time, well, you can see the whole trace of everything that ever was on the stack frame inside of this picture here. Okay, so that's how that thing executes. Now, why is it able to handle lists of size, 2 million or 20 million. So here I was with a list of length 8. What's the largest number of things that were on the largest number of frames that were on the stack at any given time? So here I had, at some point I was down here executing on this thing, and at that point there was 1, 2, 3, 4 stack frames. Yeah? And that's not the only time that happened, because later I came and I was executing over here, and there were these 1, 2, 3, 4 stack frames. Those were all functions that were still executing. And later it happened again here and here and here. Okay? So, in this case, the length of A equals 8, and there were never more than 4 stack frames at once. Okay? Or another way of saying that, the way I've been saying it, is the recursion depth is less than or equal to 4 at any point in time. Okay. What if I had instead given an array of length 16? How high would the recursion depth get then? Yep, 5. Because if I give you an array of length 16, well, the first thing that I do is I break it into 2 arrays of length 8. So if I wanted to show you what it looked like on an array of length 16, it would look like this. And everything that happens under here would be exactly the same as before. And then there would be another tree just like this one on this side, but the numbers would be different. But it would have exactly the same shape. So if I take length 16, then I get depth 5. Yep.
So how would you calculate the maximum recursion depth for this function?
Well, so the easiest way to do it is to just say, now you have to start thinking about some abstract, where have I seen this kind of function, this kind of thing? And very roughly speaking, what happens is every time I make a recursive call, it's on something half the size. So that means, I start with 1 million, then it's 500,000, then it's 250,000, then it's 1/8 of a million, then it's actually less than 100,000, and so on. So in mathematics terms, if I say, let's say the length is n, the length of the array is n, and now what I keep doing is I keep dividing it in half. So take n over 2, and then n over 4, and then n over 8. That's what happens each time I make another recursive call, is the value of n divides by 2. And this finishes when n is less than or equal to 1, right? Those are the base cases. So how many times do I have to divide n by 2 before I get a value less than or equal to 1? Anybody know of a function that behaves that way? Maybe in like an advanced functions course you took in high school. Maybe like in the calculus course you may be taking now. In calculus it's not as, that interpretation is not obvious, but really for us as computer scientists, the working interpretation of logarithms should be exactly that. Log base 2 of n is equal to the number of times I can divide n by 2 before the result is less than or equal to 1. It's not a perfectly formal definition, but for all the typical ways we use it in computer science, this is the most useful working definition. Because this is a trick that we always do. We cut things in half, make them half the size, and then recurse. And then we want to know how many times did we have to recurse? Well, the answer is log base 2 of n. Okay? And you may not be familiar with this function, but I mean, over here I've got n, over here I've got log base 2 of n, so if n is equal to 8, then log base 2 of n is 3, if n is 16, log base 2 of n is 4, if n is 1,000,000, log base 2 of n is 20, if n is 1,000,000,000, and this is approximate. Log base 2 of n is 30. If n is 1,000,000,000,000, log base 2 of n is about 40. So even if I were to give this thing an array of length 1,000,000,000,000, the recursion depth wouldn't be more than 40. Maybe 42 or something. There's a sort of off by 1 thing happening here. But Python can handle recursion depth up to 1,000. So 40 is not a problem for it. In fact, this particular implementation of Summer 3 won't give me stack, will never generate a stack overflow for any length of a list that I will give it. And I'm very certain of that because I know in order to give it a list whose that would cause a stack overflow, the list would have to have length about 2 to the 1,000. So how do I know someone's not going to give me a list of length 2 to the 1,000? Because that's more than the number of elementary particles in the universe. So even if every atom in the universe was acting as a memory cell, there wouldn't be enough of them in there to hold that list of length 2 to the 1,000. So I'm safe with this version of this thing. Okay. So this log function, it's probably not the first time you've seen some kind of logarithm. It's very slow growing, and it's a very useful, powerful tool that we use in computer science. And the way to interpret it, the way to think of it is, how many times can I divide something by 2 before the result gets small? And 2 here is just because that's log base 2, but you could also put a 3 here, and then you'd be asking how many times can I divide by 3? Super slow growing function. It's not exactly always upper bounded by a constant, but you can say, yeah, it's upper bounded by 40. You're not going to see a log n value larger than 40 in anything that you're ever going to do. Okay, so that's a good place to break today.